Alright, so today I'm going to be explaining this important paper with the title ENADPool, the edge node attention based differentiable pooling for graph neural network. So this paper in 2024. Graph neural networks are powerful tools for graph classification. One important operation for graph neural networks is the downsampling or pooling that can learn effective embeddings from the node representations. So in this paper, we propose a new hierarchical pooling operation, namely the edge node attention-based differentiable pooling for GNNs to learn effective graph representations. Unlike the classical hierarchical pooling operation that is based on the unclear node assignment and simply computes the average features over the nodes of each cluster, the proposed ENADPool not only employs a hard clustering strategy to assign each node into a unique cluster, but also compress the node features as well as their edge connectivity strength into the resulting hierarchical structure based on the attention mechanism after each pooling step. As a result, the proposed ENADPool simultaneously identifies the importance of different nodes within each separated cluster and edges between corresponding clusters that significantly addresses the shortcomings of the uniform edge node-based structure information aggregation arising in the classical hierarchical pooling operation. Moreover, to mitigate the over-smoothing problem arising in existing GNNs, we propose a multi-distance GNN MDGNN model associated with proposed ENADPool operation, allowing the node to actively and directly receive the feature information from neighbors at different random walk steps. This is the architecture of the MDGNN model associated with the proposed ENADPool. So we know that for the else layer of the diff pool that I've explained in a different video, first employs a specific GNN model to generate the node embedding matrices Z, and then generates a soft node assignments based on Z. And the node feature assigned to the same cluster and edge connectivity strength between two corresponding clusters are merged into coarsened graph structures by directly summing up them. The assignment matrix are used to form the new coarsened node feature matrix and a coarsened adjacency matrix for the next layer. To further consider the importance of different nodes belonging to the same cluster and extract more effective hierarchical coarsened graph structure information, the ABD-pool operation has made further improvements based on diffpool and employs a dot product attention mechanism to calculate self-attention, queries, keys, and of course this has a kernel version as well. So let's say K between any query and any key. We call it something like linear attention, which is an effective transformer which is used for many effective transformers. This idea that we replace it with a kernel. So let's carry on. Then the aggregated weights of the nodes within each cluster is determined by the sum of its correlation coefficients with other nodes. Unfortunately, ABD-pool cannot identify importance of edge-based connectivity between node clusters when the ABD pool generates the new quotient adjacency matrix. And so what is the proposed method? The proposed ENAD operation, we define cluster-based hierarchical ENAD-based pooling. We can simultaneously identify the importance of different nodes in each cluster and different edges between the corresponding clusters based on the attention mechanism after each pooling step. The computational architecture of the proposed ENADPool for each L layer mainly consists of 3 steps. First, the input graph of each layer, we assign a set of nodes into different separated clusters, resulting in a hard node assignment matrix. Second, we assign different ice nodes belonging to the same cluster with different weights. Through the node attention, based on the node attention, we compute the weighted compressed node feature matrix of the resulting quotient graph. Third, we assign different ij edges between the i's and j's nodes in the p's and q's node clusters respectively, associated with different weight throughout the edge attention. Based on the edge attention, we compute the compressed adjacency matrix. So the hard node assignment can deterministically assign each node into a unique cluster, and the hard assignment matrix can be computed based on soft assignment matrix. Then you get that one half of that, it becomes hard. So you got the idea. The process of a computation step is shown in the figure 2. Specifically, we propose to compute attention-based importance of different nodes over the entire graph and then normalize the importance of the nodes assigned to each individual cluster. The input is a set of node embeddings computed by a specified GNN model. So where Z sub I is the embedding vector of the ice node, N sub L is the number of nodes, and D sub L is the dimension of each node embedding for the Lth layer. So the importance of ith node in the whole graph can be calculated like this. In order to aggregate the nodes belonging to each cluster, we need to normalize the attention-based importance of all nodes assigned to the same cluster. This can be accomplished by applying a softmax function and a specific calculation process. The resulting node matrix, which is this one, can be computed by row-wisely concatenating all the quotient node embeddings. So we know which node the attention based is calculated to see which node is more important, and then you get the concatenation. So that's it, the process of aggregation of the nodes for the quotient graph through node attentions. So first we get the hard assignment, very hard assignment. There is no fuzzy thing, so always one node belongs to one cluster. After that, we aggregate nodes with attention. Of course, they also introduce the edge-based attention, but the idea is the same. This is the process of aggregating the edges for the quotient graph through edge attention. I'm wondering about the generalizability of this approach, because it's too much about learning, and I don't see any global topological things that they have used. So for the input graph adjacent matrix X, we employ a mask mechanism to filter the connections in A. This reminds me mask transformers. When it's just not attention, you have one by one inner product of Hadamard product with the mask matrix as well, so that it looks like a hierarchical attention. So, but here it's very similar. To this end, we commence by computing a family of binary matrices, and the ij's entry satisfies this. So H varies from 0 to H. And R equal to 1 indicates that the random walk departing from I's node can arrive in J's with H steps. So it's a particular factor of the graph kernel diffusion. If you remember, we have kernel diffusion is defined like this. For example, if I is 5, it means 5, a random walk of 5, of length 5. So this creates some to a graph, very conservative global topology. It gives very good information. And here there are, RH is just for the, when I is equal to H. And then they make it binary. So now that we have got a binary object, binary matrix, so it indicates that the random walk, of course, they may also include less than H steps in their H walk steps. So we compute another family of binary matrices. Now, this time they clip it with Rx. The clip is used to restrict the range of the values to be between 0 and 1, and U equal to 1 indicates that the walk step value of random walk departing from I's node and arriving in the J's node is exactly H, at least H. So in other words, UH indicates the H-hop neighborhood nodes. Oh, this is exactly mask attention transformer. Very similar to that idea. Because what they are doing, they one by one multiply by that. So it's multiplying this mask U to this power of the adjacency matrix at layer L. So you see, all these ideas are related to each other. Then they concatenate for different representations, because we construct a new topology T sub H. So this is the T that is going. It's not the ordinary adjacency matrix. It has some global information. So it is richer than the ordinary adjacency, because it not only has powers of adjacency, but also you are marking it with some mask, which make it more look like a substructure. And you are representing the substructures. You are learning to represent the substructure, let's say. So this idea has been since invention of mask attention transformer, but now people are using it for graph. And this paper for hierarchical graph pooling. So ideas are very limited, but it has huge applications for different tasks. So, we have as I said, we have a kernel diffusion, theta I, A to the I. For the second hop, n hop, all of them give us some information. So we add and concatenate them. So we concatenate them. Once we get a concatenation, then we have a good representation. But of course, there are many problems of how you keep it into memory, and is it effective or not? Do you need a low-rank approximation? There are many things that may cause it even more efficient and more practical, because sometimes these are not practical for bigger graphs, more complicated graphs that have more complicated topology, local structures. And they got the, for protein is 77, and this is attention mechanism and nodes and edges for validating the impact of each module on the basis of hard cluster-based assignment and MDGNN.